Surprising flattening of nascent gas planets. Basically, every planet begins life in a rotating vortex of gas and dust, an infant cradle that astronomers call a protoplanetary disk. However, it turns out that it may be much easier to simulate the dynamics of such disks using computers on Earth than to observe them directly. The results of such simulations may be surprising. Two scientists from Britain's University of Central Lancashire, UCL, have used a supercomputer to better investigate how exactly planets form there. It turns out that newly born gas worlds can be very strongly flattened at the poles. Observing protoplanets that have just formed but are still within the protoplanetary disks is quite problematic. So far, only 3 such young protoplanets have been registered, 2 of them belonging to the same system, PDS 70. At the moment, there are over 5,500 known extrasolar planets in the Milky Way. Where do these disproportions come from? Finding baby globes is difficult for several reasons. First of all, you need to find star systems that are young enough. They must be close enough for our telescopes to be able to detect and isolate the planet's distinctive signal, for example, spot the planet's faint light and distinguish it from that coming from the region of the disk in which it is embedded. Another issue is time and statistics. From a cosmic point of view, the entire process of planet formation takes only a few million years. This is much less than the lifetime of an average star, and even than the time it takes the Sun to fully orbit the center of our galaxy. On an astrophysical scale, this is only a brief moment in the life of a planetary system. In practice, this means that we have to be very lucky to catch a baby planet at the moment of its birth. This is largely why astrophysicists value fast supercomputers, machines capable of performing trillions of operations per second. They allow, using appropriate software, to digitally recreate distant space conditions on Earth. Adam Fenton and Dimitris Starmatellos from UCL carried out such simulations to determine the gas properties of protoplanets under different thermal conditions in their cradle, or disk. Modern simulations have such a high resolution that they allow following the evolution of the virtual protoplanet from a very early stage, when it is only a condensation of matter in a disk. In this case, the computing power of the British astrophysical supercomputer Dirac was used. To prepare an astrophysical simulation well, you need to have excellent knowledge of the physical processes actually occurring in the simulated system. In this case, a basic knowledge of planet formation is necessary. The currently widely accepted theory of their formation is the core accretion model. First, a solid core of the planet, composed of rocks, ice and other heavy substances, gradually builds up. And when it is massive enough, and about a dozen times larger than Earth, it begins to suck large amounts of gas around itself and onto itself from the protoplanetary disk surrounding it. Star, eventually forming a gas giant planet. This scenario, the so-called bottom-up process, could take several million years. A competing idea for planet birth is a top-down process, in which gas planets can form directly in a gravitationally collapsing cloud of gas in a disk, somewhat like stars. In this model, the disks around stars are gravitationally unstable. As a result of this instability, they divide over time into fragments, clusters of matter, which become denser over time and eventually evolve into planets. The core accretion hypothesis has been studied for a long time. we know that it can answer many questions related to the formation of the solar system. On the other hand, the top-down model and disk instability better explain the existence of some exoplanets discovered in recent decades. The scientific attractiveness of the top-down scenario also lies in the fact that planet formation in theory occurs very quickly, within several thousand years, which is in turn consistent with observations indicating the presence of exoplanets in very young circumstellar disks. Fenton and Starmatellos therefore used this model in their simulations, focusing on gas giant planets formed as a result of disk instability. Typically, several planets form within the disk. Simulations showed that these protoplanets have the shape of an oblate spheroid, similar to the famous NfNNs. They are therefore not spheres, and their growth involves sucking in disk gas mainly through their polar, not equatorial, regions. Newly formed gas giants can apparently be highly flattened because they are formed by the compression of material within an already flat structure such as the protoplanetary disk, but also because of the way they rotate within the disk. Technically, the planets of the Solar System are also oblate spheroids, but their oblateness is slight. For the record holder in this respect, Saturn, it is as much as 10%, but in the case of Jupiter it is 6%, and for Earth, only 0.3%. For comparison, the typical flattening of protoplanets created in the team's computer simulation was up to 90%. Such strong flattening affects various properties of protoplanets and will have to be taken into account when interpreting their future, actual observations. Flattening is not something given forever. The cores of the protoplanets that will eventually transform into gas giants as we know them are much less flattened, only by about 20%. Astronomers suspect that they will become much more spherical over time. To the simplest approximation, Earth and other terrestrial planets, including those orbiting other stars, are still spherical. Globes like Earth and Mars cannot form as a result of disk instability. Rather, they form by slowly combining, clumping together, dust particles into pebbles and rocks, then kilometers-wide objects, and eventually full-fledged planets. They are too dense to flatten significantly even when they are just forming. So there is no way the Earth could have ever been flattened to this extent, even when it was young. Supporters of all flat Earth concepts will also find no basis for their ideas in this case. Research conducted by British scientists confirms the role of disk instability in certain types of planetary systems. We are currently moving from the era of discovering exoplanets to the era of their precise characterization. New telescopes being built today will probably help discover more protoplanets embedded in disks. Observations of these young planets are slowly becoming more and more realistic thanks to existing observing instruments, such as the James Webb Space Telescope, the ALMA network or the Very Large Telescope. The predictions of computer models are also becoming more precise. The power of supercomputers and the ability to compare theoretical models with observations also bring us closer to a better understanding of the origins of our solar system. The description and results of the research were published in the journal, Astronomy and Astrophysics Letters. A new way to measure gravity. Record measurements. Physicists have managed to detect a weak gravitational pull for an extremely small object with a mass of less than a millionth of a kilogram. This achievement was made possible by developing a precise way to measure gravity at these smallest scales. This research allows us to better understand how gravity behaves in a subatomic world where quantum principles dominate. How does gravity work on a scale so small that it borders on the quantum realm? Perhaps this can be determined once we develop a way to measure gravity at the microscopic level. Physicists from the University of Southampton, in collaboration with scientists at several other European institutions, including researchers from Leiden University in the Netherlands and the Institute of Photonics and Nanotechnology in Italy, have managed to detect the weak gravitational pull acting on a very tiny particle. They did this by developing a special technique that allows them to observe processes occurring on unimaginably small scales. The description and results of the research were published in the journal, Science Advances. It is not entirely clear how the force discovered by Isaac Newton works in the tiny quantum world. European physicists have used a new technique to detect a weak gravitational pull acting on a tiny particle. They claim that this may pave the way to combining the theory describing phenomena related to gravity with the description of the quantum world, i.e. the quantum theory of gravity. For now, it is not clear how to find a common physical language that would describe well both phenomena occurring on a very large and very small scale. Tim Fuchs from the University of Southampton admitted that the results obtained by his team could help find the missing piece of the puzzle in our picture of reality. For a century, scientists have tried unsuccessfully to understand how gravity and quantum mechanics interact. We have now successfully measured gravity signals at the smallest mass ever recorded. Which means we are one step closer to finally understanding how it works in tandem, Fuchs said. The scientist added that in subsequent experiments they will reduce the mass of the particle being the target of the measurements. By understanding quantum gravity, we could solve some of the mysteries of our universe, such as how it all started and what happens inside black holes. Perhaps it will all be possible to pack it all into one big theory. Fuchs emphasized, science still hasn't fully understood the principles that govern the quantum realm. Particles and forces at this smallest scale are thought to interact differently than larger-sized objects. Gravitational effects at the smallest scale were observed in an experiment that used levitating magnets. For the experiments, the researchers constructed a sophisticated superconducting trap, cooled to 100 millikelvins and made of tantalum. The trap was placed in an advanced shock-absorbing system whose task was to dampen any vibrations that could affect the obtained results. All this equipment was surrounded by extremely sensitive sensors and enclosed in a cryostat. This sophisticated configuration also included a wheel from which brass weights were suspended. As the wheel with weights rotated towards and away from a levitating test particle composed of small magnets weighing 0.43 milligrams. A weak attraction of 30 atton-newtons was measured. 1 atton-newton is a trillionth of a newton. The mutual gravitational pull of objects of such low mass has never been measured before. The gravitational force between two objects depends on their masses and the distance between them. The larger and closer together they are, the stronger the attraction. When you start spinning the wheel, the particle will start moving, a bit like a seesaw. The force of gravity pulls it in, then releases it, then pulls it back in, Fuchs explained. It is definitely not quantum gravity yet, but it is a big step in that direction, he added. We are pushing the boundaries of science, which may lead to new discoveries about gravity and the quantum world. Our new technique, which uses extremely low temperatures and devices to isolate particle vibrations, will likely prove to be the future of quantum gravity measurements. This will help us discover more secrets about the very structure of the universe. From the smallest particles to the largest cosmic structures, said Hendrik Ulbricht from the University of Southampton. The DART spacecraft's impact changed the shape of the asteroid. In September 2022, the DART spacecraft hit the asteroid Dimorphos. This intentional collision was intended to change the object's trajectory, in the first test of Earth's defense against the threat of asteroids from space. The test was successful. Moreover, according to recent analyzers, the shape of the asteroid could have changed significantly as a direct result of the impact. On September 27, at 1:14 a.m. Polish time, telescopes around the world focused on the Dimorphos asteroid to record a historic test of our ability to defend the Earth against a potentially planet-threatening asteroid. It was the first experiment conducted by humanity that aimed to change the trajectory of an object in space. The DART, Double Asteroid Redirection Test, probe hit the asteroid Dimorphos, a small body only 160 meters in diameter. Dimorphos is a moon of a larger 780-meter diameter rock called Didymos. None of these asteroids threatened Earth, but they were considered an ideal target for testing the possibility of changing the trajectory of a space object. This was the first successful test of planetary defense in which an asteroid's orbit was modified by impacting a spacecraft. The refrigerator-sized DART probe, weighing less than 600 kilograms, hit an asteroid the size of the Great Pyramid of Giza at a speed of 22,500 kilometers per hour. Before impact, Dimorphos took 11 hours and 55 minutes to orbit Didymos. Analysis of data collected by ground-based and space-based telescopes showed that the DART spacecraft changed Dimorphos' orbit by 32 minutes, shortening it to 11 hours and 23 minutes. This result is much greater than expected. Now scientists have observed intriguing consequences of the DART spacecraft's impact. Their analyses show that the impact was so strong that it changed the shape of the asteroid. Simulation results based on Dimorphos observations showed that the asteroid consists of loosely connected rock fragments and contains many empty spaces. In other words, it is a gravitationally interconnected pile of rubble, and we should not expect to find an impact crater on it, because it has changed its shape. The material that makes up Dimorphos is so loose that the impact caused the entire asteroid to rearrange itself. And no crater was created because the entire asteroid changed or reorganized around the impact site. The research results were published in the journal Nature Astronomy. Not all asteroids are the same. They differ in composition, origin and orbit. Some of them are smaller and larger fragments of rocks, such as pieces of planets stopped in their development as a result of impacts and divided into smaller fragments. But some of them are piles of rubble flying in space, consisting of quite a large number of smaller and larger stones loosely connected to each other. This is the so-called asteroids with a rubble structure. Their characteristic feature is that a large part of their surface is simply occupied by empty space between the rocks that constitute it. This structure has serious implications for planetary defense projects and suggests that this type of asteroid will be more difficult to neutralize. Dimorphos was closely watched both before and after the DART spacecraft's impact. It was the first mission of its kind, and scientists were not entirely sure what its effects might be or what the impact itself might say about Dimorphos. A team of astronomers led by Sabina Raducan from the University of Bern in Switzerland focused on simulations, not observations. Researchers tried to reproduce the observed impact effects in simulations. Scientists estimated the number of boulders that make up Dimorphos, which gave some idea of the object's density. This data was collected by the DART spacecraft moments before impact. Combined with other data, scientists determined that it was an asteroid with a debris structure, similar to the Ryugu and Bennu asteroids that visited Earth's samplers. Didymos is also a debris asteroid, and Dimorphos is believed to be an accumulation of material ejected by Didymos during its spin or collision. According to this formation model, some of this debris remained in Didymos' orbit, and over time it plumped into a pile of debris that NASA struck with the spacecraft. For this reason, Dimorphos behaved in a very unusual way after being hit. Essentially, the impact ejected some material from the asteroid and changed it for good, but without leaving a crater. According to scientists, the material from which Dimorphos was created is so loose that the impact led to a change in the orientation of the entire asteroid. But no crater was left because the impact site was later filled by other pieces of debris that were part of the object. The asteroid's rubble structure means its surface is constantly changing. This phenomenon has already been observed by astronomers. When the OSIRIS-REx spacecraft touched the asteroid Bennu to collect a sample, the robotic arm sunk into its surface, into the loosely held material that makes up the object. The European Space Agency plans to send a probe near the Didymos and Dimorphos systems and conduct detailed research. This mission was named Hera. Thanks to it, astronomers want to closely examine the consequences of the DART mission impact. They are confident that Hera will find a transformed asteroid rather than a crater. This has implications not only for our understanding of the continuing evolution of binary asteroid systems, but also for the objects themselves and how scientists plan for any upcoming asteroid redirection missions. Since the DART spacecraft likely caused global deformation of Dimorphos, we can infer that similarly formed objects are easily reshaped and their surfaces are relatively young. Overall, the results of this study provide valuable information for understanding the formation and characteristics of binary asteroids, and will inform future searches and efforts to deflect their trajectories, the scientists write in the publication.